Hello everybody and welcome back. In this tutorial we're going to be covering quiz number 27, which is titled Single Degree of Freedom Systems. Now I was excited for this quiz because single degree of freedom systems, like the terminology of it, the definition of it, it's really simple. So I'm thinking, oh great, this is going to be a nice, simple, easy quiz. However, upon inspecting the quiz, I basically learned that this is Introduction to Dynamics. Now, dynamics is a very advanced topic. When we talk about dynamics of structure, so if we're talking about a building or a bridge, this is grad school level stuff. So you guys, of course, are not expected to know all about dynamics. The goal of this is to show you kind of the basics of dynamics and little fun facts that you guys can use going forward. So this created a little bit of a problem for me because how do I show you guys the introduction to dynamics without making this video 5 hours long? Dynamics itself is a very long topic, a very advanced topic, but of course, you guys are not expected to know the advanced things. You guys are just expected to know kind of the simple little fun facts. So the theory of this quiz is going to be a little bit different. I'm going to write it down. I'm not going to go through any PowerPoint slides or anything like that. Just to show you guys kind of the simple dynamics, what to expect from dynamics, and what exactly dynamics is. So again, probably not expected to know all of this crazy stuff, but hopefully by the end of it, you guys can take the little fun facts away from it, and using those fun facts, you guys are able to solve the quiz problems. All right, hopefully that sounds good to you guys. Let's jump into the theory. All right, guys, welcome to the theory. Again, this is actually quite complicated dynamics, very complicated subject, but hopefully I can break it down into 3 parts. And after these 3 parts, you guys can understand both the quiz, how to solve the problems, and maybe just have a basic understanding of dynamics. So again, this is a complicated issue, a complicated subject. So if you guys don't quite understand, don't worry about it. I don't think that you guys need to really know in-depth dynamics at all. So the first thing that I want to discuss is what we're actually talking about in this quiz, and that is what is a degree of freedom. So before we even jump into dynamics, let's talk about something called degree of freedom. So it's going to take me a little bit longer to write doing the theory, but I think that this will help. So degree of freedom, but we commonly express it as DOF. So if you guys look at the title of this quiz, it's actually called Single Degree of Freedom System. So degree of freedom, something we definitely need to talk about before we jump into the dynamics portion. So the first question I'm sure a lot of you guys have is, what exactly is a degree of freedom? Well, these are the degrees of movement in a system. So for instance, I'm going to take a very simple degree of freedom, and let's say that I have a cantilever beam. So what I'm going to do is I'm going to have a nice fixed support like this, and then we have a beam coming out like this. And let's say that it is subjected to 2 loads. Let's say that we have a nice vertical load at the end like this, and let's also say that we have an axial load like this. So this would be a little bit tricky to solve, but you guys aren't expected to solve something like this. This is just for illustrative purposes, if you will, for degree of freedom. So let's say that after these loads are applied, the beam is going to deflect something like this. And no, I don't want you auto-correcting. Let's try that again. I want to try and make it look somewhat nice. Oh, all right, hold on. 3rd time's the charm. I just can't hold it for as long. Let's say it deflects something like this. And of course, this is not to scale, or probably doesn't look like anything we actually expect. But here's kind of the gist of what a degree of freedom is. If we're looking at this deflection, and we'll go to green, we can see that we can express this deflection in terms of 3 different things. So if I'm looking at this point at the end of the beam right here, which is now this point over here, we can see that 3 things happen to this point. One is it had a vertical translation downwards, so this would be considered 1 degree of freedom. The second one is it has a horizontal translation over here, so this would be another degree of freedom. And then we can also see that it rotated. So what I'm going to do is I'll put something like this to say that it rotated. This is another degree of freedom. And before we move on, some of you guys may be saying, Clayton, what do you mean by it rotated? Well, if we look at the beam originally, the cross section is nice and horizontal, but after the deformation, the cross section is now angled. So in this type of system, what we say is there's 3 degrees of freedom. One of them being vertical translation, one of them being horizontal translation, and then of course one of them being rotation. So this is what a degree of freedom is. It's basically just what ways can this particle or element move. Now when we're talking about single degree of freedom systems, as you guys may have guessed, this means it's only moving in one direction. So what I'm going to do is I'm going to come down here, And what we're going to do is we're going to talk about now single degree of freedom. So what I'm going to do, single DOF, single degree of freedom, which is the title of this quiz. Now, the most simple single degree of freedom system that we have, of course, is going to be a mass on a spring. So what I'm going to do is I'm going to draw, let's say that we have a fixed top here. Let's say that we have a spring. So it comes down vertically, and then my nice little spring movement, and it comes down a little bit more. And at the end of the spring, we have a mass. So we usually throw it just as a box, and we'll say that we have a mass M. Now, the reason why we call this a single degree of freedom system, and I'll change colors here, is because the movement here is solely going to be vertical, thus only one single degree of freedom. So when we deal with these type of systems, we're expecting this mass to go up and down, but we're saying this mass is not going to go horizontal and this mass is not going to rotate. So since we only have one direction, which is vertical, we say that it is a single degree of freedom. And this is actually how we do a lot of our structures. As you guys will see later in structural dynamics, if you guys take it in grad school, we express a lot as single degree of freedom systems. Now, that is what a single degree of freedom system is. Basically, we're only considering one direction of movement. If you guys think of your basis sets where we have E1, E2, and E3, a single degree of freedom would be simply saying it's only moving in E1. There's going to be nothing in E2, and there's going to be nothing in E3, something like that. All right, so that's single degree of freedom systems. So now let's move on to the second topic, which is going to be dynamics. So now that you guys know what a single degree of freedom system is, this will make a lot more sense when we start talking about topic number 2 here, which is dynamics. And this, again, crazy topic. You guys are probably not expected to know too much about this. So let's go back to the same system that we had before, except I'm going to make it just a little bit bigger, like this. So we have this. We have a spring coming downwards, and I'm not very good at drawing springs, but I'm sure that it'll work for this illustrative purpose. So we have a mass on a spring, and this is always going to be the key to dynamics, a mass on a spring. Now for dynamics, this is what we're basically saying. So we have this mass here, and let's say that we pull it down. So let's say we take this mass, we pull it down, and what's going to happen is we're going to release it. After we release it, we know it's going to go up and down, up and down, up and down, and slowly going to keep going until it eventually stops. Now, this point at which it stops is what we call dynamic equilibrium right here. So again, I'm going to draw a line here, and this will be dynamic equilibrium. And again, to show you guys exactly what's happening, I can pull this down, and what's going to happen is this mass is going to vibrate about that equilibrium until it eventually slows down and stops at that equilibrium point. So that's what's going to happen. Now, this is where things get a little complicated because we try and model this movement. And this movement can be expressed by the following equation, where we have our mass multiplied by the second derivative of displacement, so this would be acceleration, and then we add it to something called c multiplied by the first derivative of displacement, so in this case, this would be equal to velocity, and then plus the stiffness of the system multiplied by displacement. And then what this will all be equal to is our applied load, which I will call F at t. Now this becomes a problem because everything's in terms of time, and time is going to play a big factor in this. So the first thing I want to kind of talk about really quick is what is this term right here, because this is a term that you guys will not be getting into at all, but it's very important to understand. This term right here is associated with damping. So that's what we call it, damping. And what does this mean? Well, it means if I pull this down, it's going to vibrate about equilibrium. But with every oscillation, it's slowly going to get smaller until it stops. Okay, that's very important. Because let's say that we didn't have this term in here. We neglect this c term right here. So we have our mass times acceleration plus our stiffness times our displacement. What would happen is when I pull this down again, it's going to start oscillating, but it'll never start decreasing. It'll oscillate forever. It'll never start losing energy, stuff like this. So that C term is going to be very important. However, like I said, we don't really use it in this course because damping is actually something that's not very well understood, and it's actually causing a problem for a lot of research. A lot of research is spent trying to figure out what that C term is in relation to damping. So the first thing that we're going to discuss is something called free vibration. And this basically means that we're going to ignore damping and we're not going to apply a load. So our new equation becomes this, where our, oops, I don't want the highlighter here. Let's switch it to a different color. Let's go purple, where we have our mass times our acceleration, so the second derivative of our displacement, plus k, which is our stiffness of our spring, which I guess I'll put over here, multiplied by the displacement is equal to 0. So this is the most simple case of dynamics, and this is exactly what I said, where I'm not applying a force to this spring, or sorry, this mass. I simply pull the mass down with my hand, and then I let go. So of course, when I pull it down, and then I let go, we know it's going to start oscillating up and down, just like this. And since we're ignoring the damping, of course, it's not going to stop. It's going to remain like this forever. All right, so that's the kind of the first thing that we have. And what happens is we look at this equation, we say, all right, this is simply a differential equation, and we can solve for this differential equation. So what I'm going to do is I'm going to come down here, and I'm going to show you guys the solution. So in this particular case, our displacement as a function of time is going to be our original displacement at time is equal to 0. So this would be the amount I pulled down the spring, and this would be multiplied by cosine, and then a factor which we're going to talk about, which we call omega n, and then this is going to be multiplied by t. And then we have a second term, which is going to be the velocity at time is equal to 0. So again, if I'm pulling it down and I hold it there and then I let go, this velocity is going to be equal to 0. And this is divided by that special term, omega n, which again we'll talk about, multiplied by sine of omega n t. And if you guys take dynamics, this will basically be the first equation that you guys deal with. So again, let's just move a little bit forward and let's extend this to the case where I take my mass, I pull it down, and then I let go. So if I pull my mass down, then it actually at our time is, or sorry, our displacement at time is equal to 0. Well, that'll be the amount I pull it down. Now, if I hold it there and keep it still and then release, well, we know that the velocity at time is equal to 0 is going to be 0. So just to kind of illustrate dynamics a little bit further, we're going to say that this term goes to 0. Therefore, we can ignore everything here. So therefore, our new equation becomes this, where our displacement as a function of t is going to be equal to u naught, so this is the amount I pull my spring down before I let go, multiplied by cosine of omega n t. So if we look at this equation, well, we can kind of visualize what's happening. I'm pulling a spring down, which will be my u at 0, and then I'm multiplying by cosine of something times t. So t makes sense, that's just time. The only thing that we don't really know is this omega n. Now this omega n is actually called the natural frequency of our structure. So when we're calculating our structure, the first thing that we want to do is always find this natural frequency. What is it equal to? Well, it's equal to the stiffness, which is called K, divided by the mass, which is simply m right here. So as we can see, our displacement as a function of time is going to be both reliant on our stiffness of the structure, so how stiff it is, which is basically EI and an L term, and then also the mass. So this is one thing that we have to keep in mind. In our normal structural analysis, we don't consider the mass. We usually just consider the stiffness, but now we're actually considering what that mass is. So what we can do is we can say, all right, well, if I'm interested in the velocity of the system, or the second question in the quiz, which is going to be the first derivative of this, we can simply take the derivative. We get u naught multiplied by wn times the sine of omega n times t. Now, there might be a negative here. I'm not sure. I'll include a negative. Why not? I'm not the best at taking derivatives because this is the key that I want to show you guys. So for the second question, where it's talking about how does the mass influence the speed, well, we can see that if we increase our mass down over here, we can see that our natural frequency starts to decrease. Now, if we look at the equation for velocity and our natural frequency starts to decrease, well, therefore our speed will also decrease. So when we get to question number 2 and it's asking about the speed, we know that if we increase the mass, we start decreasing the speed or the velocity of the system. All right, so that's going to be question number 2, and this is what I wanted to show you guys about free vibration. So the second thing I also want to talk to you guys about dynamics, and this is going to be very important for question number 1, is loading rate. So this is something that you guys will already see or kind of already be able to visualize, hopefully, and this will make sense. So I'm going to come down here and we're going to call this section right here loading rate. And this is going to be kind of the key takeaway. And this is something that I want you guys to remember, because if Dr. Simon were to put anything like this on a final or midterm, it would probably have to do with loading rate. So what we're going to do is we're going to take a nice simple example. So what I'm going to do is I'm going to draw a beam. And no, this is not a bridge beam relating to the example. This is just a regular beam. And let's say that I apply a load right at the midspan of this beam of, I don't know, let's just call it load P, because it doesn't matter how much the load is. We know that this beam will deform something like this, and I'll try and move the curve. That doesn't look very good. All right, let's try again. Something like that. Does that look? Oh, that's not what I wanted at all. All right, so but you guys get the gist of it. The beam's going to deform something like this. Now, in our current analysis, what we do is we say that this deflection right here, this midspan deflection, we call it the static deflection. So we say it's U, ST. So that's static deflection under the load P. So what I'm going to do is I'm going to do a very nice plot here, and this plot should hopefully answer a lot of the questions when it comes to loading rate in dynamics. So what I'm going to do over here on the y-axis is I'm going to have the ratio of my dynamic deflection compared to my static deflection. So what I'm going to say is I'm going to have u as a function of t divided by that static deflection. So that static deflection is something that we've already know. This is something we've dealt with so many times. And I can see that my one axis is not very nice at all. So I'll just make this a little bit nicer. All right, there we go. So you guys see where that static deflection comes, something like this. And on the x-axis, what I'm going to do is I'm going to define it as TR, and I'll show you guys what TR is in a second, divided by TN. So this TN right here, this is the natural period, and it's simply 1 divided by the natural frequency, so it's not that hard to calculate. But this is, and I'll highlight it again just to make it really clear, this is a property of the structure, okay? So this is going to be a property of the structure. So if we're dealing with the same structure, we don't really have to worry too much. Now, in our static case, this is the response that we expect. Oops, I don't want the highlighter. All right, give me a second, guys, technical difficulties. We expect this to go from 0 all the way up until our load, nice and linear, and then we're going to just stay there. So this right here is when we reach that static deflection. So if we're looking at our dynamic deflection, this will occur at a value of 1. So basically we're increasing P until it hits that maximum value right here. And then since we just keep P there, our deflection stays the exact same. So this is the static case, and this is what you guys know. Now, if we were to consider the dynamics of the structure, this response actually changes depending on our loading rate. So let's talk about a really slow loading rate. If I were to apply my load to a structure very slowly, so the load increases very gradually over time, what I'm going to expect is a response like this. So it's going to be a sine curve, or a combination of sine and cosine curves, and it doesn't really change. And as you guys will see, it basically mirrors that static deflection right there, so it looks pretty nice. All right, so this is if I apply the load nice and slowly, and generally speaking, this is what happens in structures. We don't have to worry about dynamic effects too much. Now, on the off case that there's an earthquake, that load gets applied really fast. And what happens is if we apply that load fast, we actually get kind of the following response, where it kind of goes like this. So the amplitude of those sine curves or cosine curves gets magnified. Now here's the kind of the keep away, and I'll go back to the dotted line. In a faster loading rate, we can actually experience displacements that are greater than those static displacements. So let's say that if I applied the load mildly, so it's pretty fast, but it's not extremely fast, I might get a dynamic displacement of 40% greater than the static displacement. Now here's the key. If I were to apply the load extremely, extremely fast, I'm going to get something like this. Something crazy like this. So if I were to just punch something really fast, I'm getting that crazy load. Now what happens is if we start approaching where it's basically just an impulse and the load's getting applied as fast as possible, what we're going to find out is that this load approaches 2 times the static deflection. So this is going to be the key here. And it's a pretty simple takeaway. The faster we apply the load, the more deflection we will experience. The slower we apply the load, the more similar it will be to the static case. So what I'm going to put down here is I'm going to say, all right, well, if we apply fast load, and this will be something that you guys want to write down for your midterm or something like this, fast load, our displacement, which we call U at t, it approaches 2 times that static displacement. All right, and on the other hand, if we do a slow load, what we find is that our U of t, or our dynamic displacement, it actually is pretty similar to our static displacement. So that's the key here. And it's pretty simple, as you guys may know. We load something faster, we're going to get more displacement. If you guys forget about this, it's simple. Take a really heavy book, put it on your desk, and then slowly load it. As you guys will see, it moves very slowly. However, put that same book on your desk, smash it with your hand. As you guys will see, well, hopefully you guys don't hurt your hand, but as you guys will see, that book will move a lot faster and experience more displacement. All right, so this right here, and I'm going to highlight it, and it says that I had the highlighter on the dotted. I guess that looks kind of funny. This right here is going to be the takeaway that you guys are going to want for your midterm and your final right here, because this will help us solve any questions you may experience, as well as the questions in this quiz. So let's go down to the quiz questions really quick. The first one is probably the hardest of the two. It says, a spring mass system was shown to vibrate about the equilibrium position such that the maximum displacement is twice the equilibrium displacement. So that's what we talked about before. If we load something faster, it's going to have twice the displacement as the static case. It says, in the design of structures, the dynamic effect is taken into account by multiplying the stresses within a structure by a dynamic, I can't even say dynamic, by a dynamic factor, normally between 1 and 2. And again, this is because that displacement, the maximum would be 2, the minimum would be 1. So it's going to be somewhere in between there. It says, given 2 bridges, one longer than the other, which one would have a higher dynamic factor? All right, so this makes, this is kind of a tricky question, but it makes sense in the fact that if we have 2 bridges and we have our load, which should be basically a car driving across the bridge, what we're going to do is we're going to look at this load traveling across the bridge. So of course the car is going to start at one end, and it's simply going to drive across from vroom all the way to the other side. Now the key here is if we look at the shorter bridge, the time it takes for this load to get to the support to the center of the beam, which is the maximum load, is going to be a lot shorter than the longer bridge. So if we were to look at the car on the longer bridge, it's going to take a lot longer for this car to travel to the center of the beam, which is something, let's say there. So from here, we can say that this smaller beam right here, or this smaller bridge, it is loaded faster. So we're going to put faster right here. And as we just talked about above, something that's loaded faster tend to experience a lot more deflection. Therefore, in this particular case, we're saying that the shorter bridge would have a higher dynamic factor. Now, this is something I want to clear up to you guys, but this is out of the scope of this course. This is not always going to be the case. The key assumption that we made here was that our natural frequency, Wn, which is equal to the square root of the stiffness of the structure divided by the mass of the structure, was the same for both of these bridges. All right, we assumed it was the same. And if it is the same, then everything comes down to loading rate, which we say, all right, the shorter bridge is loaded faster, higher dynamic effects. However, it makes sense that one bridge being a lot longer than the other, the natural frequency of these bridges would actually not be the same. And if that's the case and we don't know the natural frequency of these 2 bridges, we actually can't conclude anything. Because not only is it dependent on loading rate, it's also dependent on natural frequency. However, in this question, we're just assuming that the natural frequency of the 2 bridges is the exact same. And therefore, we can just conclude it based on loading effects, all right? But then keep in mind, if you guys are doing design, this natural frequency will play a big factor in your guys' design. As you guys will see, if you take the 479 capstone project. But actually, some of you might be taking it next semester. For that, I wish you good luck. All right, let's move on to the second question. Second question is even easier. It's what we talked about above, where we said assume that a spring mass is vibrating under dynamic equilibrium. So again, I have a spring, I pull it down to an initial displacement, and I simply let it go, and I watch it vibrate up and down. It says if the mass is increased while the stiffness is kept constant, then the following happens to the speed of the vibration. As we talked about above directly, we said that if we increase that mass, so if our mass is increased, therefore our natural frequency omega n is actually decreased. And if we decrease omega n, well then our speed will also decrease. So the correct answer for number 2, the speed of the vibration will decrease, which will be part B right here. And that's it to this quiz. So if you guys look at this quiz, if you guys don't know dynamics, it's actually a real bitch. Let's be honest. This quiz is not the best. It kind of sucks if you don't know dynamics. Luckily for you guys, Dr. Sammer is very nice, and he's just testing basically the concepts of dynamics. And the concepts are pretty easy. Omega n, as you guys know, it's simply the root of k divided by m. So if we have a question that changes the stiffness K or the mass M, it's very easy to determine what happens to the system. The second thing we talked about was loading rate. And again, that one's even easier. If you guys load something faster, you guys will get more displacement. And you guys can see that in everyday life. Just smack something with a hammer, watch how fast it moves compared to if you slowly push it. All right, hopefully that sounds good to you guys. That's it for this quiz. And I just want to apologize. I know that this is probably one of the worst quiz videos ever. Again, because I'm trying to take something that's so complex and simplify it very simply for you guys. So if you guys don't know dynamics by the end of this video, good. You guys aren't supposed to know dynamics by the end of this video, but hopefully you guys got the little fun facts such as loading rate and what happens to speed, stuff like that. All right, guys, thank you so much for listening. I really appreciate it. I will see you guys in quiz number 28.